All right, thank you very much for the introduction, and thanks a lot to the organizers for the invitation and the opportunity to give a talk here. It's a great pleasure to be here in Vienna. So today I will talk about some aspects of the study of transitive actions of free groups and Baumslag Solitar groups. This is a joint work with Alessandro Carderi, Gaboriau, and Yves Stalder. And basically our motivation comes from ergodic theory, where we started to look at what's called non-free measure-preserving actions. And we realized that, well, not much was known in this direction. And one of the most basic questions that arose in our study was, okay, I have a non-free action on a probability space, and then I can look at the action on each orbit, and this is a transitive action. And so actually, in order to tackle these questions, we really needed first to look at transitive actions of free groups. And, well, I will also mention later Baumslag Solitar groups. And it turns out that, and I hope I will convince you that there are interesting, very basic questions one can ask in this setup. Okay, so let's start. So if we are given a countable group gamma, I denote by subgamma its space of subgroups. And this is a subset of the power set of gamma. And this sits as a closed subset. So it is a compact Polish zero-dimensional space. And we have a natural gamma action on it by conjugacy. And so the action, let me write it down properly. Gamma dot lambda is just gamma lambda, gamma inverse. Okay, and the point is I want to here give a different flavor on this space by viewing it in a different manner. So equivalently, when I have a subgroup of my favorite group gamma, I can, from this I get what I will call a pointed, this yields, sorry, let me rather call it rooted transitive action. So what is a rooted transitive action? It's an action on a set X, where x0 is some fixed element of X, which I will call the root. And I want the action is to be transitive, so let me remind the definition. I want that the gamma orbit of x0 is the whole set X. And so what's the connection is that, from lambda subgroup of gamma, I have this natural pointed, rooted action on the coset space gamma mod lambda, and I have a favorite base point, which is just the coset corresponding to lambda. Okay, so this takes me from subgroups to rooted transitive actions, and the other way around, if I'm given a rooted transitive action, I can consider the stabilizer of my base point x0. Okay, and the point is that this correspondence gives you a bijection between isomorphism classes of rooted transitive actions and the space of subgroups. And in this talk, it would be important to, we will present things with using rather this point of view. Okay, and now so on this space of subgroups, we had this conjugacy action. And now we can view it more naturally somehow in this setup by just saying that gamma times the isomorphism class of a rooted transitive action is just the isomorphism class of, well, it's the same action as before. Maybe I give it a name. And you just shifted your root using your element gamma. And so these are really the same action. I mean, this connection is equivalent if I put this action on the space of isomorphism classes of rooted transitive actions. Okay, so now let's talk about the topology under this correspondence. So for this, it would be easier for me to assume that gamma is finitely generated. So let me pick a generating set S, which is finite. And now from an action, a rooted transitive action, we can build what's called the Schreier graph of the action. So what is this? So it's, as a graph, it has multiple edges, and it's an oriented graph, and you can have multiple edges from between the same vertices. But the vertices are just formed by elements of X, and the edges, you put an edge from X to S times X, for every X in X, for every S in S. And this is actually a labeled graph. So to label this edge by S. Okay, so let me just give two quick examples. So let's take as gamma the free group on two generators generated by, say, A and B. You have the trivial action. And so this has just one point and two loops. And I have the labels like this. And I have also the free action, which gives you this picture that you all know, where here I have A going horizontally and B going vertically. Okay. So let me just mention that in this picture, so the two examples that I have given, they correspond to the following subgroups. Here, my lambda is the whole free group, and for the free action, the stabilizer group is just the trivial group, okay? And so in this talk, I will be interested in kind of opposite situation. These two groups are normal subgroups, and in particular, if I view things geometrically, this means that wherever I put the root, I always see the same graph. And in this talk, again, we'll be interested in a different kind of behavior. But okay, let us go back to our initial question of understanding the topology. So what does it mean by the sequence of subgroups converges to lambda? Lambda n converges to lambda. This means that whenever I fix a radius r, positive radius, then for large enough integers, when I look at the ball in the Schreier graph of the action onto gamma mod lambda n. And I take as a center of this ball lambda n. And I look at the R ball. This is isomorphic as a rooted graph. So when the root is this thing, this is isomorphic to the ball. Where here I put lambda instead of lambda n. Okay? So this is a geometric way of understanding convergence in our space of subgroups. And this is really just I mean, this is an easy exercise, but it's an important one. And so now that I have said that, I can state what is the focus of this talk. We will study the gamma action on this space of subgroups for two groups. The first will be the free group on two generators, but the same kind of things goes for finitely generated free groups. And the second class of example will be this Baumslag Solitar groups. So I'll just say what these are. And I'll focus on what's called the Baumslag Solitar group with parameters 2 and 3. Okay, so transitive actions of the free group, you can think of them as, well, actions, I mean, as giving you two bijections, and you ask nothing of them. Here you want to ask something. So I will give you the definition by generators and relations. So my group is generated by two elements T and B. And the thing is that T conjugates B2 to B3. Okay, so this is the group. And it's quite famous because it was the first example of a non-Hopfian group, so it has a surjection onto itself, which is not an injection. Okay, so this is what we want to do. Study this dynamically. So the first thing that we can see is that we can restrict to the perfect kernel. I mean, in order to have something interesting. So what is this? Let me remind you that you have the Cantor-Bendixson theorem, which tells you that given a Polish space X, there is a largest, and then it's necessarily unique, closed perfect subset, which I will denote by K of X. And perfect means that you have no isolated points. And let me just remind you that one kind of constructive way of proving this is just by removing isolated points and keep doing that. And the point is that you have to do this over a countable ordinal, but after countably many steps, you will actually arrive at this perfect kernel. Okay, so here is. Sorry?
X is compact.
You don't need compactness.
Then you have to remove countable sets, not isolated points.
Sorry?
Then you have to remove countable sets, countable open sets, not isolated points.
You remove the set of isolated points may be countable, yeah, in general. Here I'm in a compact, so it's always a finite set that I remove. But it's a finite open set, which is why this will have to stabilize after less than omega-1 steps. Okay, so here is our first proposition. So, okay, no, sorry, before that I have to make a small observation. is that if gamma is finitely generated, actions on finite sets are isolated points. Or if you prefer, I mean, if you rather like the subgroup point of view, the subgroups of finite index are isolated. So the way to see this is just, well, if you look at this topology, you see that an action on a finite set is going to be completely determined by its restriction to a large enough ball, which is why you have this isolation property. Okay, and now let me state our first result. The perfect kernel of this is simply all infinite index subgroups, or in terms of isomorphism classes. So the isomorphism classes of actions with X infinite, and then it's countable, of course. And same thing for this BS2, 3. Okay, so the space of actions on infinite sets, so the space of infinite index subgroups. And one observation that I want to make is that we show that this is also the space of, BS2, 3 action, where there are infinitely many B orbits. And the point of this second description is that it carries over to arbitrary M and N, where both M and N are of absolute value different from 1. Anyway, this is just a side comment. Okay, so now we have removed these isolated points. So the next question is, well, what about the action on this perfect kernel? So we were very surprised that it had not been looked at before. So, and I mean, maybe we missed something, but so our second result is the following. So the action of F2 on this perfect kernel has a dense orbit. Sorry? Ah, okay, sorry. Is it okay? Yeah. Okay, so this action has a dense orbit. So we actually gave a name to these guys with a dense orbit. We call them totipotent. If so its orbit is dense. In this, okay, let's do this just for F2 for now. Okay, so totipotent, actually, it comes from biology, where you have, these cells which can become anything if they are young enough. And the point is that geometrically, if I come back to this picture here, these are actions where, if I look at any transitive action on the free group on an infinite set, I look at a certain ball. Well, this ball is going to appear somewhere in the Cayley graph of my action. So in particular, I mean, this action, it cannot be, for instance, it cannot correspond to a normal subgroup, but much more than this. For instance, such an action is automatically faithful. And okay, let me just mention this. It's also automatically amenable in the sense that it has arbitrarily large, almost invariant sets. But really, I want to just explain here this faithfulness. Faithfulness means that you have every non-trivial group element acts non-trivially somewhere. And why is this true here? Well, simply because one of your balls has to be a ball corresponding to this, to the trivial subgroup. So in particular, if you give me a particular group element gamma in the free group on two generators, well, I view it belongs to a large enough ball in this, and then I see that this guy has to move some point because I have to see large enough balls of the Cayley graph in my Schreier graph. Okay, so let me just sketch the proof of this. And actually, yeah, I will just use a new blackboard. All right. All right. So let's see why this is true. So the point is that by Baire category, you only need to show the following. You're given an action alpha 1 on x1. So this is, sorry, f2. And another one, which is transitive. Both are transitive over infinite sets. You need to find an action, again, a pointed transitive action, which has somewhere one ball. So yeah, maybe I should also fix a radius. And I want to find an action alpha 3, which has one ball, one R ball, like that of alpha 1, centered at x1, and one R ball, which is like that of alpha 2, centered at x2. Okay, so I have something like this. This is my ball for my action alpha 1. This is my ball for my action alpha 2, and these actions are on infinite sets, so transitive on infinite sets. So in particular, I know that I have some edge which goes out of this ball. Okay, this is a ball. I've said that. So this is just a fixed ball of radius R, centered at this x1 and here at this x2, and I want to build an action which somehow amalgamates these two things. Well, this is very easy. I just say, okay, I can get out of this ball, and let's say that I get out with A here, and to make things more difficult, let's say that to get out of this action, there was also an A edge like this. Then what can I do? Well, I can just connect these two actions with a B like this. And then, okay, I don't have an F2 action yet because the action is not everywhere defined, but then I can extend this to be as free as possible. Namely, I mean, I just put the Cayley graph of the free group wherever there are missing things. So like if I have a B here, I will start putting A, B, and then I will get, so I do this on all the points where the action is not defined. And the point is that I still stay in my perfect kernel, so I still have an infinite action, an action over an infinite set, which is transitive. So, okay. So this is how you can prove that there are totipotent actions. And now I want just to compare the situation. Oops, that was a bad move. To compare the situation with Baumslag Solitar groups. And I will call this pluripotency, which is a weaker property of cells. So I will focus on now gamma is BS to 3. And here the point is that we get a different phenomenon. So I just need a bit of terminology. I will denote by Q the set of integers such that n is prime with 6, which is the product of 2 and 3. And then what we show is that there is a partition of the perfect kernel of gamma as follows. So this is a disjoint union over Q in Q of this, what I will denote by KQ. Disjoint union, some guy which we call K infinity. And these guys, they are open gamma invariant. And this guy here is closed gamma invariant. So always for this conjugacy action. And each AQ infinity contains a dense orbit. Okay, and let me just finish by telling you just what is this KQ a bit more precisely. So what's the point? Let me maybe remind the defining relation. This is TB, TB2, T inverse equal to B3. So one of the first observations you can make is if you're given a transitive action of this group, you can look at the B orbits, and if one B orbit is infinite, then all B orbits must be infinite because your graph is connected, and the only way to go from a B orbit to another is to use this T, and this T conjugates B2 and B3. So B2 has an infinite orbit, and then B3 as well. And so you can propagate this infinite thing. And so the reason why we have to look at this Q here is when B has a finite orbit, then you have some simple arithmetic going on. And you see that when you do this connection, well, you cannot change. If you look at a B orbit, you cannot change. You remove the prime factor, the powers of 2, the powers of 3, and you see that this is an invariant when you conjugate by T, and this is why you have this phenomenon. Okay, and so my time is up, and I'll stop here. Thank you.